fun paper, Emergent Hierarchical Reasoning. Kind of continues the thread that we've been talking about a couple weeks now, reflective of the fact that more and more people are kind of exploring hierarchies. Um, Makes a lot of sense why we would want to do this. Hierarchies present a way to explore the reasoning space more efficiently, more diversely. They also seem to be reflective of human reasoning in some hand-wavy patterns. Um, and this is yet another approach. I think, like all approaches before it, we're gonna find some things that don't make the most sense, but I think overall I really like the paper. So I hope you guys enjoy it. The link is in the Discord. Um, okay, so this was a paper from HKUST, Tsinghua, University of Waterloo. And like most of these reasoning papers, they kind of start out by saying, oh, well, the human hierarchically reasons as like, here's like a vague picture of the human brain, and we have kind of the prefrontal cortex that's being highlighted, and then, really the highest level of decision making. I have this problem. Um, and they ask the question, how can we induce this in models? And like, what does this tell us about models' ability to solve problems and get problems correct and reason on their own? Um, so first of all, their whole thing is kind of premised around kind of flat reasoning threads. So this is kind of a reasoning thread we might be very familiar with, a very standard reasoning thread from a model like Quen or something. And what they notice in this reasoning thread is that there are some phrases, like these blue, any of the colored phrases are kind of indicative of what they call a plan. So these are planner tokens. And then the black tokens are kind of the execution of that plan. That's their basic premise, that if we could just identify which tokens kind of signal that the model is thinking hierarchically or thinking in a planning oriented mode, then we can do something to tweak their emergence or tweak their kind of greater explorations by the model. Um, they talk about a couple different kinds of plans, although they don't really touch on it for the whole rest of the paper. But um, just to help solidify this notion, I mean, they talk about logical deductions. So all of the light blue, you know, let's look at. I noticed that are kind of planning tokens that indicate that the model is about to start doing some logical deduction. They talk about branching, so the darker blue are are kind of planning tokens that indicate that the model is about to try something different, or maybe consider two different approaches at the same time. And then they also consider backtracking, which is kind of a planning indication that the model is about to revise what it's been reasoning about, maybe take a couple steps back. And then if you think about the search space, it's going to kind of go towards a different branch of the search space. Okay, so like that's their premise. I mean, people talk about hierarchy in many different ways, so I think it's good to establish that this is their view of hierarchy, that we are not talking about a hierarchical, variable generation process or something. We are just talking about some tokens are indicative of plans and other tokens are indicative of executions. Now they have a couple of observations about like standard reasoning models before they introduce their algorithms. And these are all pretty interesting. So I think it's useful just to like go through their observations. I mean, these are what they use to kind of premise the need for hierarchy. In general, what they will argue through this section is that like the learning process in RL-based reasoning models follows two phases. The first phase, which is these ones over here, are what they call procedural consolidation. So procedural consolidation, they define as like the model is learning how to execute. Given a plan, the model is learning how to go forth and execute that plan. So like if the planner token says, you know, I need to backtrack, I need to consider something else, the execution portion would then go off and consider that. And they show in a couple figures that we're going to get to that we can kind of observe this by looking at token level entropy. So in general, their hypothesis is that as the entropy or as the distribution becomes more diffuse over tokens, that is an indication that well, it's an indication that multiple things are happening, but from an execution standpoint, it's an indication that the model does not know how to execute. But as the entropy drops or as the distribution becomes more spiky on a couple of tokens, that's an indication that the model is learning how to execute. So it has less uncertainty about kind of how to go about the procedural steps. After this occurs, then they say the model is getting better at strategic exploration. So it's kind of a two-step process. First, we learn how to execute, and only after we learn how to execute do we then learn how to plan better and generate planning tokens better. And we're going to see some more specific plots later. This is kind of an illustration, but they're also going to look at entropy changes, entropy increases, but they're going to look at a different kind of entropy increase. So they're going to look at the entropy increase over just the planning tokens. And so their observation is that like as entropy increases over the planning tokens, that's an indication that we're learning to explore more. So we're learning to consider different plans and we're learning to plan more at more different stages. Um, yeah, so let's dive into the actual results that they're presenting in this section. I mean, one more thing to say is that they kind of argue, they make their case through correlations. So they say that this entropy decrease is correlated with this task accuracy increase. And they also say that the entropy increase for planning tokens is correlated with sequence length increases in the generation. So this is a kind of a result, as you recall from the R1 paper, that as RL continues, the sequence length of the reasoning threads are increasing. And so they're holding that up as evidence that planning is increasing, that we are taking more steps in the search space. And so this is the correlation that they use to kind of make their point about um, planning tokens. Okay, so we've talked about planning tokens for a bit, planning tokens versus execution tokens. The first thing to establish before we actually dive into real results, the first thing we need to establish is how do we actually identify planning tokens, right? So they call a planning token, they call this a strategic gram or a strategic engram. And as we saw before in the kind of colored phrases, um, the strategic grams are engrams that indicate that we are trying to plan something. We are trying to take a higher level view to coordinate um, the next set of execution tokens. So these are examples of strategic grams. So, let's define a helpful subproblem, let's backtrack and revise. And here are examples of regular engrams. Um, plug this value into 5.5 times x is y. Um, and they kind of have a very like hacky way of describing engrams. And this was one of the more, or this was one of the less convincing parts of the paper. But you got to start from somewhere. So basically, they they extract all engrams from all reasoning threads, from successful reasoning threads. They take successful reasoning threads, they extract all engrams. Um, I think their premise overall are that planning tokens are general across problems, but execution tokens are specific to specific problems. So their hypothesis is that if you look at n-grams that occur throughout reasoning threads, then you will be identifying planning tokens. You'll be identifying strategic tokens. Okay, so they take n-grams across all reasoning threads, they embed them and they cluster them, just to say, look, there are different ways to express the same planning objective, uh, and we can kind of generalize it a little bit by clustering. They don't really talk about how many clusters they use, but yeah, imagine we can start to identify these clusters. After that, they take clusters that are kind of only present in the top 20%, in the most that are most present, the top 20% of clusters across all documents. And then they just merge all of these n-grams together. So the strategic gram set is composed of all n-grams that are in the top 20% of clusters across documents. They don't do any validation, but they do show kind of some of their n-grams in the appendix, and they are kind of n-grams like this, uh, these kind of higher level n-grams. So we kind of have to assume at some point that this is kind of a valid hypothesis. Okay, so now that we know like what strategic grams are and how to differentiate strategic grams from execution level grams or non-strategic grams, we can look at entropy and perplexity over just these strategic grams compared with other grams. So these are their actual results. Remember, phase one is procedural consolidation. Phase one says that the entropy and the perplexity will decrease for all tokens and then it will stabilize. The general claim here is that this is the phase in which RL is learning how to execute. And so we see this. We see this for both planning tokens as well as execution tokens. We see a decrease in perplexity in general, and we also see decreases in entropy. Um, and pretty crucially, kind of execution tokens for entropy, they stay very low throughout the training process. But in some cases, the kind of entropy of the planning tokens will increase towards the end of the training. Um, so they say that token level entropy in general, token level entropy is dominated by execution tokens just because there's a lot more execution tokens in overall in the reasoning threads. Um, and then they're going to make the claim later that kind of semantic entropy targets strategy. Semantic entropy is they will define as entropy that is just targeted on the planning tokens. So these curves are defined as semantic entropy, the red curves. I was a little confused for a second when I was trying to parse these plots, um, that perplexity and entropy were flipped because their general claim is that uh, entropy over execution tokens decreases, and then it's kind of a signal of consolidation, uh, which is totally valid. We can see that here, but then we can also see that perplexity stays higher than planning token perplexity throughout the entire curve. So that was a little confusing to me, but I take that as an indication that um, kind of higher perplexity but lower entropy indicates spiky distributions. So you can have perplexity is all about kind of the chosen token. Um, how confused is the model about the actual next token that was observed? And if you have high perplexity, it can still mean that your distribution is concentrated on two or three or four tokens. That would be really low entropy if you have like a very heavy distribution on a couple of tokens. But you can still have high perplexity if your chosen token is a third or the fourth token, right? Um, so if anything, kind of this observation further solidifies the fact that like the probability distribution is becoming more and more concentrated uh, in general, even if the execution token maybe isn't always the most preferred token. Okay, so now in phase two is their strategic exploration phase. That's where they say the model learns to plan better and learns to explore the search space better. Um, so they draw this phase by saying that the semantic entropy, or as we defined in the previous slide, the entropy just over the planning tokens, the semantic entropy will increase, which correlates to accuracy increasing. And they show this in a couple of different, across a couple of different models. Um, and as you can see, we do have a pretty clear correlation. As semantic entropy increases, accuracy is also increasing. Um, Sequence length is also increasing. And they kind of say this has been missed before. This has been missed by previous analyses um, because the entropy of other n-grams has always stayed low. So if we just look at average entropy, it's way harder to see this correlation. Um, yeah, does that make sense to everyone?
Yes, it does.
Okay, so that's their depiction of what is happening in the reasoning process. Okay, this is just one of their final observation plots. They're showing before everyone was just looking at the token entropy or token probability distribution. Um, this is always going to be dominated by common stop words or n-grams that are very common, and so they will obscure the effects that we're trying to look at. Uh, so whereas on the other hand, if we're just looking at strategic grams and their frequency, we will find much more interesting strategic grams, and we will find much more interesting kind of dynamics, training dynamic, and entropy dynamics over these strategic grams. And yeah, so intuitively, we've just been looking at the wrong thing this whole time, is what they claim. Okay, so their takeaways, just to summarize this section, procedural consolidation is marked by a sharp decrease in complexity and token entropy. Um, the model quickly builds a reliable toolbox of procedural skills, allowing the frontier of performance improvement to shift to higher level strategy. By the way, their paper was so uh, AI written, it wasn't even funny. There's like so many little AI written segments you could tell. Anyway, takeaway two, once the payoff from procedural consolidation diminishes, performance gains are driven primarily by exploring high level strategies. That was the phase two that we looked at. Um, Finally, takeaway number three, aggregate token level entropy kind of obscures the point. So its token level entropy is dominated by lower level execution tokens. So as the model becomes more confident, the entropy in these tokens naturally decreases, and our global average is totally thrown off by these tokens. So we've been looking at the wrong thing this whole time, which now leads them to propose their HICRA algorithm. Their HICRA algorithm is very simple. This is standard GRPO, uh, where the advantage function over a trajectory is calculated by the reward of that trajectory minus the group average of a bunch of different trajectories, right? A bunch of different roll out 10 trajectories for your question. calculate the reward average over those trajectories, you have GRPO. They make a very, very simple adjustment to GRPO. They just say in general that if your token is in a semantic gram set, is in the set of semantic grams, then add this absolute value. So they set alpha to 0.2. So like add 20% of the absolute value of your advantage. Otherwise, use your regular advantage. What does this do? Well, if your token is a strategic gram and your reward is one, if you got the problem correct, then you'll have a higher advantage. You'll have a more positive advantage. If you got the problem incorrect, you're just going to have a less negative advantage because it's still the absolute zero, the absolute value. Uh, I just want to walk through an example quickly. So let's say we have three trajectories, um, for the same question. This trajectory ultimately was correct, and these two were wrong. Our standard GRPO, we would take the reward for each one, so 100 here, minus the group average. The group average for all three is 1/3. And so we would get an advantage of two thirds for the first one, negative 1/3, negative 1/3 for the next two. Um, and our batch total advantage across all five tokens would be 3.33, negative 1.67, negative 1.67. Right? Pretty standard stuff. Now, let's say that these two tokens, let's plan steps, branch and rethink and backtrack, are semantic grams. Then these tokens would have correspondingly more advantage in all cases. So in the positive case, they would have a little bit more positive advantage. In the negative cases, they would have a little bit less negative advantage. Does that make sense to everyone? Um, yeah, actually, this image was generated by GPT, so it was pretty cool. This was not in the paper. Okay, so the takeaways, this is from the paper. The takeaways, the policy is incentivized to explore the subspace of strategic plans more thoroughly. This leads to faster discovery of effective reasoning patterns. And when these strategies yield high rewards, the amplified average ensures they are strongly reinforced. So I think that this is, I want to pause on these takeaways for like 1 second. Because when I was reading this paper and I was like reasoning through their HICRA algorithm, I was thinking, well, wouldn't this just like influence just more planning tokens in general? And couldn't this have a negative effect? Like, couldn't this just lead us to spend so much time planning, like overall, because we're just rewarding them more? Um, but I think that point number three really addresses that because yes, it will lead you to plan more, but then when those plans are correct, they'll get even more advantage. So they'll continue to kind of be reinforced when they actually help you. Uh, yeah, so maybe in the future, if they could extend this to have even more reward for positive rewards versus less reward for negative trajectories, maybe that would help even further reinforce the amplified advantage. But for now, this appears to work when you set alpha to 0.2. They didn't do much exploration around alpha to my knowledge. They just kind of set it at 0.2. But yeah, it seems to work. Okay, so for the results, in general, they're finding increases over standard GRPO. So and actually quite large increases. Um, it appears that their largest increases are, unless I'm mistaken, I mean, it looks like their largest increases in general are on base models, rather than the instruct models. Um, although that's not always true, but like it could just be an indication that maybe there's something else happening in the instruct models that they're not really capturing. Um, yeah, I think Llama is the only model where they had some um, decreases across multiple categories. Maybe they also had a decrease across Olympiads here in Quen. But they're going to talk about kind of why Llama was an issue. And their basic takeaway was like, Llama was kind of so bad that it couldn't even get off the ground um, in many cases. So like you see overall these scores are a lot lower. And they say like, yeah, if you can't even plan in the first place, if you can't even execute in the first place, then like these two-stage training dynamics are just never going to occur. They have some multimodal reasoning benchmarks, which is fun, just to show that this also occurs in vision models. I guess that's a bit of a surprise. I mean, we would expect that strategic grams in general would influence planning and language only models. Visual models, a little bit less clear to me where the hierarchy comes in, or I mean, maybe it's just the planning tokens in general, um, are still a very important part. But like, yeah, they are also seeing improvements for multimodal reasoning. Um, okay, so then they have a couple of different kind of analyses of their results, which I found pretty interesting. Um, so for this first analysis, they used GPT-4 to analyze reasoning threads and categorize errors that are happening in the reasoning thread. In general, their point here is that errors in planning and strategy are decreasing. So they observe that across three different models. Um, and then Quen 2.5 is kind of an anomaly because yes, the planning and strategy errors are decreasing, but also the other kinds of errors, they don't decrease as well. They also are increasing a little bit. Um, and if you notice, I mean, their error count for in general is very high for Quen 2.5, and they kind of make the point that execution errors don't decrease because maybe the error rate for plans is too high to trickle down into execution improvements. If you have an incorrect plan, it doesn't matter how well you are executing, you are still going to get a negative reward. Their second observation is uh, that targeted exploration is a lot better than indiscriminate exploration. So what are they showing here? So they're showing that uh, their algorithm leads to more exploration quicker than GRPO does, um, and that this is directly correlated to validation accuracy. So yeah, I'm not sure why they don't continue GRPO longer. Because it would be interesting to see how this curve continues to change over time. Um, but yeah, we just have to take this like delta that we observe emerging as proof that at least until training step 170 or 80, that our validation accuracy is very tightly correlated with our semantic entropy. Again, remember semantic entropy is defined as entropy over the strategic grams specifically, and not over any other grams that are generated. Their next exploration around this targeted versus indiscriminate exploration um, is the observation that entropy regularization just doesn't work. So entropy regularization is a baseline that other people have tried. Um, when they've made similar observations, they've said, okay, entropy is important. What can we do to increase our entropy? Um, let's increase a regularization term so that we kind of ensure that entropy stays high overall. Uh, but what previous work has done has been to target this across all tokens, right? So that's a good baseline for them to compare the effects of their targeted exploration because as entropy over all tokens kind of increases, that's also going to increase entropy over execution tokens. And so we can see that these light blue lines, which are entropy regularization, they're almost the same as baseline GRPO in terms of validation accuracy and certainly symmetric entropy. Uh, Whereas kind of when we target our entropy increases to just the strategic grams, then we are seeing higher validation accuracies. Let's see. This pass at 8 is kind of muddled. I guess they're trying to show that it doesn't really affect training dynamics because training dynamics are still they're kind of equivalent for all methods. Token entropy. Yeah, so this makes sense because um, if we're going to regularize entropy, of course, we're going to expect the token entropy overall to be higher. Over all tokens. Remember, stage one is kind of this learning how to execute stage. So it's going to take us longer to learn how to execute, and then we're just not really going to learn how to plan. Whereas HICRA helps us learn how to execute quickly, and then our token entropy just increases again and again because we are learning how to explore and plan better. Um, okay, I think this is one of the last ones. Semantic entropy is where exploration continues. So they are trying to show here that your token accuracy can collapse. Um, your token entropy can collapse. So this is your overall token entropy, um, but your semantic entropy can increase. I mean, yeah, pretty obvious um, based on what they've shown before. Um, yeah, what to say? I guess I kind of wonder this token entropy is cut off at training step 150, whereas the token entropy over here does change pretty dramatically after 150. Um, but yeah, I just assume that after this is when their semantic entropy is starting to dominate the entropy overall. Okay, and then the final point that they want to make is another comment on previous research. So again, they want to make the point that their strategic grams are helpful. They say that previous research has looked at high entropy tokens in general. And in general, we need to acknowledge that like they say all planning tokens are high entropy, but not all high entropy tokens are planning tokens. So they show this example here where um, the blue is just high entropy tokens that are not planning tokens. The red is, I guess, planning tokens that are not especially high entropy. And then the shared are planning tokens that are also high entropy. Um, and they show this again. Yeah, here are the proportions of high entropy planning tokens. So in general, entropy of planning tokens increases before and after training in a, in most of their models, or stays the same. But the proportion of high entropy tokens that are planning tokens, um, yeah, it doesn't necessarily increase. It kind of decreases in a couple, it increases in a couple. Um, right, so a majority of our functionally defined planning tokens are also high entropy, but the reverse is not true. Most high entropy tokens are not planning tokens. Okay, so yeah, that's the last slide. Um, any questions?
Yeah, I just wanted to ask and note to compare and contrast with the Beyond 8020 paper, which was specifically targeting high entropy tokens. But I guess the last two slides really gave the answer to that question, where they are aware of that research and they say, like, hey, our method for identifying those pivot tokens is better than their method. And I really like this diagram, which was like fourth slide from the last, I think, 23, no, 22. Yeah,
Mm-hmm.
so the left one, leftmost uh, graph on this slide, I think it gives like really, because they are defining strategic grams without using entropy at all, and then they're targeting them, and their entropy increases.
Mm-hmm.
Uh, it just seems like pretty telling as far as the training dynamics go.
Yeah, yeah, yeah. It's a good point. I mean, we could argue with their technique for identifying strategic grams, but it has nothing to do with entropy. And logically, they seem to make sense, just kind of as a spot check. Um, and then, yeah, their entropy does increase. So I think I found this kind of pretty compelling. I'd love to see, I mean, this does, I think, highlight an interesting training phenomenon. I would love to see better methods for identifying strategic grams. Um, maybe, yeah, because we could kind of like this really depends on the distribution of your training data or your reasoning data. Like you could easily imagine clusters that emerge if you have like a very mixed data set, but maybe it's dominated by chess problems or a certain kind of math problem. You can imagine clusters that emerge that are actually execution clusters that aren't actually strategic clusters. So like you have to be there's a lot of special sauce here in how they identify their strategic grams. And I think future work that maybe takes a more principled approach, like what does it mean to be strategic or planning oriented, I think could really maybe improve this even further. But yeah, for this set of strategic grams and for this problem, I think that yeah, Dimitri, you make a good point that this is kind of cool that they see this emerge.
And in the procedure for identifying strategic grams, are they using the base or instruct models, or are they using a vanilla GRPO tuned model to build the traces from which they extract the engrams?
That's a good question. I don't quite recall. I think um, yeah, I can get back to you on this. There were a couple of missing details in general, but I'll do it. I'll look. Yeah, I don't think that they mention it actually, or maybe it's in the appendix, but I'll get back to you on that question.
Okay. And a kind of similar question. So in the very beginning, there was multiple charts comparing the entropy and the accuracy and perplexity.
Mhm.
Oh, yeah, these ones. So are these ones derived from the HICRA method or vanilla GRPO?
Um, these are supposed to illustrate vanilla reasoning properties. I think they're just illustrations. I mean, they're kind of like they are the first cover photo. So
Okay.
I think that this is just an illustration of what they are trying to show. Um, there's one thing I should mention is that like they kind of make the point that this is the ability to plan and the ability to be hierarchical is they start with the premise that that is learned during pre-training. So the pre-training models have seen enough instances of humans doing planning and reasoning um, that they already have this ability. But they say that the RL process is just trying to make this ability come out, and that we can see this in these plots, but like the yeah, but we can have better ways to get this ability to actually come out of pre-training.
Okay. And then later, of course, they do have comparison plots with GRPO versus HICRA of how entropy of strategic tokens versus all tokens changes. So that makes sense.
Yeah,
Yeah,
I would
yeah.
I would note in general, like I am. I mean, looking at these again, where okay, so the entropy for the execution token stays very low throughout, which is fine. That's what we expect. But it does make me like kind of confused about these plots over here where their token level entropy in general like goes way up. Um, I assume maybe it's just the maybe Quen 2.57 base is like a little different, but like they do make the argument, they do try to make the argument in the beginning that like overall token entropy is swamping out everything that we observe with semantic entropy. So like I'm confused why this like really shoots up over here.
What is validation accuracy here?
It's just their reward, I guess, on the validation set. So yeah, if they're looking at math problems, it's like how often do they get the math problems correct?
Yeah, so there's almost no difference between it and the others. And there's a huge difference in semantic entropy and token entropy.
Yeah. I mean, this it looks like a small difference, right? But like, I don't know, they also are showing kind of these plus 5 points of increase, plus 6 points of increase. And that does count as like a big difference in the literature, right? Uh,
Yeah,
so I don't know if you squint, I guess I guess it is
yeah,
like this is also Quen 2.57b, and what do they see? Quen 2.5. 7b, yeah, it's kind of in range plus two, plus three.
On this table, Quen 3 4B looks so impressive compared to Llama 8B, and 4B is fairly small. Makes me want to experiment with it because you can literally do these experiments at home with 4B model.
Yeah, yeah, they get good results and even good results on top of results that are already very high of these.
yeah. I would echo your concerns about their validator, their choice of strategic versus um, low level tokens. It reminds me of that seal paper I did, the steerable vector, where they chose reflection, execution, and
Oh yeah.
transition
Mhm.
tokens, and then injected a steerable vector to yeah guide it using LoRa. And you could almost choose anything. They chose uh, yeah strategic, but if they put that line anywhere else, what would the results be?
Yeah, I remember that.
Mhm.
Um,
Or if they just optimize like because they're adding the penalty, right? If they just added that, or they added the reward, if they just add that reward to backtracking, or if they just added that reward to logistical reflections, how would that influence it as opposed to yeah grouping all those three into uh, strategic?
it's a good point. Yeah. Yeah, they don't even They don't even have methods to identify logical deductions, backtracking, or branching. These are just
Where an LLM could do it easily, an embedding model or yeah, something could do that quite trivially.
right, right, right. I do think that kind of some like clear follow-ons on this would be to refine the strategic gram set, and like it's kind of easy. It would be really easy to do that with an LLM. Uh, but yeah, talking about your steering vectors paper, I also was thinking that kind of I just wonder what kinds of planning steps happen that are not directly executed in the tokens. I think that I think that yeah, maybe parts of planning are not directly expressed or maybe aren't yet being expressed in these reasoning models as tokens. But but yeah, I think you raise a good point. Like they could look at each one of these individually or something else.
That paper, I think the main finding was reflection tokens and transition tokens. When the model went off, yeah, going down a bad path, those got very high. So they wanted to reduce those. And so here, if it's going down a bad path, then obviously the chain of thought is increasing. But also, I would probably say reflection and transition tokens are strategic tokens, so they would be increasing as well. So
Yeah.
is it a different conclusion from this that they saw? Well, I guess that on that paper they studied difficulty of problems. Here they didn't look at problem difficulty or cases where they went off track.
Yeah, that's a really good point. I mean, I think I would say two things. One is that um, I don't think that just like intuitively, I don't think that reflection tokens would get captured in this process because you really have to depend on like these tokens are among the most common grams across problems. So if they're like, reflecting about a specific execution thread, I would expect them to be a little bit more specific and maybe they wouldn't appear in the top 20%. Uh, that being said, yeah, they didn't look at problem difficulty. Um, but I would, okay, the last comment that I want to make on that is point number three. So they're not just, they're not just encouraging more of these tokens. Where I feel like maybe, unless I'm incorrect, I feel like the steering paper was just trying to encourage less of those tokens. What these guys are doing is that they're trying to encourage more of these tokens, but also learn the right way to use those tokens. So like they're trying to generate them more, but then reward the ones that are correct or the ones that are part of correct threads. And they're trying to say over time that that's going to lead to something more nuanced. That's going to lead to kind of a better understanding of exploration and planning strategies and all of that. So that makes sense.
Yeah, it does, and it is a division between high level and low level, where mid track, like high level, obviously at the beginning of the reasoning process, you're thinking more high level and how to do it, but you also do it in the middle of the reasoning process as well. So you want to encourage it at any time.